Hello everyone. In this session, we'll learn the symmetrical components of unsymmetrical phasors or resolution of unbalanced phasors into their symmetrical components. So before deriving symmetrical components from the unsymmetrical phasors, so let us see what is operator A, what actually does in symmetrical components. So the vector or operator A is a unit vector which when multiplied with another vector rotates that vector by 120 degrees in positive direction without changing its magnitude. That is, let us consider this is some vector. You assume it is a voltage vector we are having here. Now when this voltage vector is multiplied with an operator A, that is AV, so this will make this voltage vector rotated by an angle 120 degrees. So which makes this vector rotates through an angle of 120 degrees. Now this is the red line, we are seeing it. So when we multiplied this V with A, will rotate this vector by an angle 120 degrees. So this is your AV, this is your V. Now this is represented by A is a unit vector and the phase displacement is 120 degrees, 1 at an angle of 120 degrees, in turn represented by e power j 120. So that is nothing but the values minus 0.5 plus j 0.866. Now if the same operator is multiplied twice with a vector, so then it makes that vector to rotate through an angle of 240 degrees. Similarly, if it is multiplied by 3 times, then it rotates that phasor through an angle of 360 degrees. Now let us see when it is multiplied by twice. So what is the value? A square unit magnitude, it will rotate through an angle of 240 degrees. Now you see this is your initial vector. So when it is multiplied with A square, so this vector is rotated in a counterclockwise direction by an angle 240 degrees. So this is the position when it is multiplied with A square. So it rotates through an angle of 240 degrees. So A square is 1 at an angle of 240 degrees, that is equal to minus 0.5 minus j 0.866. Now when this operator A is multiplied by 3 times with that phasor, then that phasor will rotate through an angle of 360 degrees. So how to represent that one? A cube is equal to, so that is A square into A. What is A square? Is 1 at an angle of 240 and A is 1 at an angle of 120 degrees. So when we analyze this one, solve this one, so we will get the value equals to 1. So therefore A cube is equal to 1. Now let us see here, when we add up all these things, 1 plus A square is equal to 0. So that means what? 1 plus A square. A is 1 at an angle of 120, A square is 1 at an angle of 240 degrees. So when you expand those things and solve it, and the value will be equal to 0. 1 plus A square is equal to 0. Therefore A plus A square is equal to minus 1. So this is an important operator which is used in symmetrical component analysis. Now let us take the symmetrical components of unsymmetrical phasors. Now what happens here? Let us see here. Now this is, what is this one? This one is positive sequence component. 1 indicates, suffix 1 indicates it is a positive sequence components of a unbalanced vector. So now VA, VB, VC. So in the previous session we have taken a sequence as RYB. Anyway, here we are taking it as an ABC. So either RYB you can take or ABC you can take as a notation. So here VA1, VB1 and VC1. So phase sequence is ABC. So this is positive sequence component. Now in this positive sequence component you can see this, the vector VB1 is lagging behind VA1 by an angle 120 degrees. or in other words VB1 is leading by an angle 240 degrees with respect to VA1, isn't it? So VB1 either lagging by 120 degrees with respect to VA1, or VB1 is leading by an angle 240 degrees with respect to VA1. Now how to represent this VB1 with respect to VA1? Now you can see VB1, so it is leading. I am taking leading instead of taking lagging. I am taking leading. So you can take lagging also. So if I am taking it leading wise, it is 240 degrees. So in order to get a vector with a 240 degrees rotation, then we should multiply that vector with a square, which has been discussed in the previous slide. So therefore VA1, when it is multiplied with a square, so then it will make an angle of 240 degrees. So therefore VB1 is equal to a square VA1. Or if you are considering lagging by 120 degrees, then you can represent a VA1. So that means lagging means minus 120 degrees you should consider. Similarly, what is VC1? Is lagging by an angle 240 degrees or leading by an angle 120 degrees with respect to VA1. Now how to represent VC1? It is leading by 120 degrees with respect to VA1. So that means VA1 must be multiplied with an operator A, so that we will get VC1. Now you see VC1 is equal to A VA1. A indicates it is unit vector 1 at an angle of 120 degrees because it is leading. So when we multiply this VA1 with A, this vector will be rotated through an angle of 120 degrees. So that makes the vector equal to VC1. Is it clear? Now this is from positive sequence component. Now let us see here the negative sequence component. Now when you write the negative sequence component with respect to A phase only, so VC2 is lagging behind VA2 by an angle 120 degrees or leading by an angle 240 degrees. Now how to represent this VC2 with respect to VA2? So leading by 240, that means VA2 must be multiplied with A square. So therefore VB2, okay. So let us see here. Now VC2 is multiplied with A square VA2. Is it clear? Now VB2, if you consider VA2 with respect to VA2, it is leading by 120 degrees. So therefore VA2 must be multiplied with A in order to get VB2. So therefore VB2 is equal to A VA2. Now similarly, can you guess for zero sequence components? Because there is no phase difference or phase displacement between each vector, that is 3 vectors are there. So now all are in phase, isn't it? So in such cases, so what is the value of this zero sequence values? That is here R I have represented. So please consider this one as A, B, C. So now here all these values are equal. That is VB0 is equal to VC0 is equal to VA0. So that is A, B, C. So VA0, VB0, VC0. So this is a correction. Please make a note of it. Instead of RYB, read it as A, B, C. Okay, so VB0 is equal to VC0 is equal to VA0. So now we got a relation with respect to phase A. With respect to phase A, so we got this relation. These are the relations from positive sequence, and these are the relations we got from negative sequence, and all the zero sequence component voltages are equal from the zero sequence component. Now what we have to do? We have to substitute these values in these equations. Already we have derived in the previous session this one. So there only the difference is we have taken RYB. Here we are taking ABC as a original sequence. So we have derived there VR is equal to VR1 plus VR2 plus VR0, isn't it? But here ABC sequence we have taken it. So we replaced VA is equal to VA1 plus VA2 plus VA0. Similarly VB is equal to this equation. Similarly VC is equal to this equation. These equations already we have explained in the previous session. So whatever the relations we got it, this one, this one, this one, we will be substituting it here. So that means what? VA1, VA2, VA0 will retain as it is. VB1 will replace it here. VB2 will replace this one. VB0, it is same because all zero sequence voltages are same. Then VC1 is equal to this one. Then VC2 is equal to this one. then Vc naught is equal to Va naught. So we are going to substitute all these values in these equations. Let us see what happens here. Now we have done that one, and these are the resultant equations. After substituting those relations there, so we got these relations Va, Vb, Vc. So call those as equations 1, 2, 3. Now what you have to do, add all these three equations. So adding equations 1, 2, 3. So what we are going to get on LHS side, Va plus Vb plus Vc. So this is what we got, and all the Va1 components we are going to add. So that means what, Va1, so Va2, so that means all this one I have added up these things. So Va1, A square Va1 is there, A Va1 is there, isn't it? Similarly Va2, A Va2, then A square Va2, then Va naught, so Va naught, Va naught. So why? Because Va naught is equal to Vb naught is equal to Vc naught. So Vb naught is replaced with Va naught, Vc naught is also replaced with Va naught. So that's why all these three components are same here. So here it comes Va naught, Va naught and Va naught. So when we add up these things, now we can see here what happens here. All the red color terminals, you can see Va1 is a common here. So take it outside, Va1 common. So what is left out? 1 plus A square, isn't it? So now once after getting this one, similarly blue colored terms, if you see there, Va2, A Va2, A square Va2. Va2 is a common. If you take it outside, then it will be 1 plus A square Va2. Then what is this one? Va naught, Va naught, Va naught. All these three quantities are added up. So it will be 3 Va naught. Now in the previous slide we have seen that 1 plus A square is equal to 0. So this is 0 and this is also 0. So left out will be 3 Va naught is equal to Va plus Vb plus Vc. So from this one, what is Va naught is equal to 1 over 3 Va plus Vb plus Vc. I think you understood this one. This is 0, this is 0. 3 Va naught is equal to Va plus Vb plus Vc. So therefore Va naught is equal to 1 over 3 of Va plus Vb plus Vc. Now this is the first zero sequence component of voltage we got. Now let us derive it, the other two components from the unsymmetrical phasors. So now multiplying equation 2 by A, equation 2, multiply this one with A on both sides, and multiply equation 3 with A square, that means A square here and A square on both sides. So when you do that one, equation 2 with A and equation 3 with A square, so the resultant equations we are going to get it like this. Now you see AVB, so A into A square A cube, then A into A square Va2, then A Va naught. Similarly this equation is multiplied with A square Vc. So this is the resultant equation, we got it, 4 and 5. Now again you add equations 1, 4 and 5. Now you see adding equations 1, 4 and 5, that is this equation 1 and 4, 5. So the resultant will be this one. On LHS side, Va plus Vb plus Vc. So there is Va, AVB plus A square Vc. And on RHS side you can see A cube is 1, A cube is 1. So therefore Va1 is common. So it is 1, it is 1. So it will be 3 Va1. Then here in this one Va2 is common, taken it outside. So what is left out? 1 plus A square, 1 plus A square. A power 4 can be written as A cube into A. A cube is 1. So this is nothing but A Va2. So this is A Va2. Now coming back to here, Va naught is a common. So I have added up. So 1 plus A square. So this is what we got. Okay. Now let us see. Same thing I have represented here. Now you can see from this equation, so what happens? 1 plus A square is 0. This is also 0. So therefore 3 Va1 is equal to this equation. In other words, Va1 is equal to 1 over 3 of Va plus AVB plus A square Vc. Now this is what the equation we got from those analysis. So this is positive sequence component from their unbalanced symmetrical phasors. So next component let us obtain. Now multiplying equation 2 by a square and equation 3 by a and adding with equation 1 we get, that means these are the equations 1, 2, 3. Now multiplying this equation 2 with a square on both sides and multiplying equation 3 by a on both sides and the resultant equations adding with this equation 1. So what we are going to get now, this is the thing. So this is your equation 1 and this is a square vb and this is your avc. So these are the three equations we got. Again we are going to sum up. So after summing up and taking out, you can see va1 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 1 plus a square. So this component will be 0. Then va0 is there, which is a common 1 plus a square. This component is also 0. Now va2, that is becomes 3va2 is equal to va plus a square vb plus avc. So therefore from that one, so we will get va2 is equal to 1 over 3 of va plus a square vb plus avc. Similar to these equations, so we have derived va2 also. So we got both all the three components, that is positive sequence, negative sequence and the zero sequence voltages from their unsymmetrical phasors. So similarly on the same lines we can derive the symmetrical components of currents. So on the same lines, Ia0 is equal to 1 over 3 Ia plus Ib plus Ic. Similarly Ia1, instead of Va1, same thing, replace it with Ia plus Aib plus a square Ic. Similarly this Va2, replace it with Ia2. So Va means Ia, a square Ic, a square Ib plus a Ic. So on the similar lines, on the similar analysis you can make it with respect to current and you will get the equation, symmetrical components of currents here. Now this is how we got the symmetrical components of unsymmetrical phasors. Now in three-phase system, what happens is the sum of all the line currents is equal to the current that is flowing in the neutral. So what are the line currents here? Ia, Ib and Ic. So these are the line currents, so which are flowing through that one is equal to the neutral. So that means Ia plus Ib plus Ic is equal to the current that is flowing through the neutral. Now from this equation, what is Ia plus Ib plus Ic is equal to 3 times Ia0. So that's what we are going to get. So Ia plus Ib plus Ic is nothing but 3 Ia0 is equal to In. So therefore Ia0 is equal to 1 over 3 times of In, that is neutral current. Now these are the few, now this is the repeated one. Now these are the few references. You can go through this one. The first one, power system analysis by Hadi Sadat. Elements of power system analysis, the second one. Then modern power system analysis by D.P. Kothari and Nagrat, and all the three are McGraw company publishers. So you can go through these references for more details. Thank you.